So I was reading the news recently, and one of the news stories is that the second Voyager spacecraft left the solar system. And the way that they know the Voyager spacecraft left the solar system is because when you leave the solar system, you lose the influence of the solar wind from the sun. So that's how the boundary of the solar system is defined. And they know that because instruments on that spacecraft, which was launched when I was a teenager, still function. And they function because they have a power source, and the power source is thermoelectrics. And so I'm going to start with the subject of thermoelectrics. So thermoelectrics are a solid-state way of converting heat into electricity. And the way you can understand thermoelectrics is to think about the electrons in a semiconductor. So the electrons in a semiconductor, when you're at finite temperature, they're excited away from the Fermi energy by something of the order of kT, and therefore they have entropy, which couples to heat gradient, and they also have electric charge, and that coupling between electric charge and electric field then means there's a coupling between electric field and thermal gradient, and those are the thermoelectric effects. If you want to understand it in a more simple way, just think about a gas in a container, and if there's a temperature gradient, that means there's a cold side, and the gas particles will try to accumulate on the cold side, and if those gas particles have charge, then that will mean there's an electric field, and thermoelectric devices exploit that electric field. So what's different? Well, charge carriers in semiconductors are fermions, so when we do our Boltzmann transport theory, we should use Fermi-Dirac statistics instead of Boltzmann statistics. And also, they don't follow the parabolic dispersion of classical particles, p squared over 2m, but they follow the dispersion of the actual band structure, which we should consider. So the interesting thing about thermoelectrics, though, is that it's what we call a contraindicated property. And I think that's a phrase that I first learned at the Williamsburg workshops in the context of multi-Ferroics. But anyway, it's a property that if you look at textbooks on condensed matter physics, you think you can't have high thermoelectric performance. And the reason is because thermoelectric performance is a composite property with contradictory elements to it. So this is the metric for thermoelectric performance called ZT. And here you have electrical conductivity. Here you have CVAT coefficient, which is the coefficient that couples temperature gradient and electrical voltage. And here you have thermal conductivity. And the problem is, according to the parabolic band model, sigma and S are oppositely related. And so if you want high sigma, you should have high doping and light effective mass. And if you want high S, you should have the opposite. And unfortunately, it just doesn't work out. And then there's other contradictions having to do with the thermal conductivity. And just to make that a little bit more concrete, this is what we see in textbooks, is we see this parabolic band model. This is the density of states of a parabolic band model in 3 dimensions. And if you take into account the normal behavior of scattering, electron-phonon scattering, you find out that there's no way to resolve this conundrum that you want high conductivity and high thermal power. So this is a real semiconductor. This is old data for gallium arsenide. And if you look at N-type gallium arsenide, then it kind of looks parabolic here, but there's other pockets nearby that might have some influence at very high temperature. But if you look at P-type gallium arsenide, what you see is that there's nothing parabolic about it. So here you have a cubic material, and you would need a mass that depends on direction to describe this band, which would be symmetry forbidden. And so you can see that in real materials, the parabolic band model should be taken with some caution. So I want to begin by talking about Can I use this?
Maybe. He told me to come in here and change the battery in the mic.
Okay.
No, it's
Do
the
that?
other mic. The
So,
mic.
does this help anything? I can't really tell.
Is it on?
Does this help? Yes, I can tell. Okay, thank you. So I want to start with lead telluride. And lead telluride is a material that was used in spacecraft. It wasn't used in Voyager, but it was used in Pioneer. Voyager was based on silicon germanium. But it's a material that's been known since the 1950s. And it has a figure of merit at that time known to be ZT equals 0.6. But recently people have done a lot of work on lead telluride-based materials and have discovered that by various modifications, the performance can be very much higher than that, higher than 2 actually. So we also were interested in that and became interested in what was special about it. And the first thing that's special is the band structure is unusual. And I'm not going to dwell on band structures in this talk. I'm going to talk about dielectric properties and ferroelectricity more. But I just want to show you that. So this is the band structure of lead telluride. And so it has one pocket here for p-type at the L point. And it's pretty non-parabolic, as you can already see by looking at this dispersion. And you can see it better if you look at the density of states. 0 is the valence band maximum, and then as you go to higher binding energy, you're moving down in this picture. And you can see an onset of a very high density of states at 0.2 electron volts. And that's really why lead telluride becomes such a good thermoelectric, and especially because of the nature of that. So lead telluride is a cubic material, but the nature of that onset is that the carrier pockets at the L point interconnect via these tubes, and these tubes are a two-dimensional object. They're in a network, and so because of that network, overall it's three-dimensional, but it's a kind of a dimensional reduction, a topology change of the bands caused by that interconnection, and that's the origin of the high performance of lead telluride. In other words, that you can, in this direction, it looks like a very light mass material, but in this direction, it looks very heavy mass in that particular tube, and therefore you can resolve these kind of conundrums. So that's part of the story, but that's not the whole story. So here's the other part, or at least one other part of that story. So lead telluride is almost a ferroelectric material. So these are phonon dispersions that we calculated for lead telluride, and it was known before this to be almost a ferroelectric material. So if you substitute lead by tin, it becomes a ferroelectric at low temperature. It's a high conductivity material, so it's very difficult to measure. And if you substitute by germanium, then it's a ferroelectric material at high temperature, again difficult to measure. And I first learned about that at this meeting from Karen Rabe in Williamsburg, who presented first principles calculations and models for germanium telluride. Anyway, so this is a phonon dispersion of lead telluride that you can calculate. It's quite delicate as far as methods go, but this really is sort of the low temperature energy of the polar transverse optic mode in lead telluride. And then, as is not surprising to people in this audience, I also learned about this at the Williamsburg workshop. There's a strong pressure dependence of ferroelectric modes in many materials, and lead telluride is no exception, although that wasn't previously studied. And so what you see is that the ferroelectric mode strongly increases in frequency as you compress the lattice. And that got us to thinking, because the other component of a good thermoelectric is low thermal conductivity. And up to then, although people knew about lead telluride, which has a very low thermal conductivity, the focus was on using